Okay, sorry for the delay. Hopefully we will not face any autofocus problem here. So I just want to wait a little bit for you to be able to join. Okay. So there were two problems left from the previous session before starting, so that people have time to join. I will write it on the board so you can think about them in the meanwhile. So one problem was to calculate, I wanted to find primitive functions for the following functions. So let me write this example here. So this is still the old lesson. I will start a new lesson today now. Determine all primitive functions of the following function. All the primitive functions of each item, of each function. So number one, f of x is equal to 2x divided by x squared plus 1. I still see that there are only 14 people online, so are you facing some problems? I would appreciate if someone can share the link to everyone. I posted the link. Oh, okay, thank you. Thank you very much. Okay, so this, I want you to know about this. I saw some exercises in the book somehow uses this idea, okay? Even though it's not standard at this level, but because of those problems, level 3 problems, I want you to know also about that. And of course, it's not beyond your math knowledge. So here, in principle, what you need to do is to do some guesswork again. Okay, because the systematic treatment of these kind of problems is called method of substitution, and you will study them separately, systematically when you go to university. But it doesn't mean that you cannot solve this. But if you want to solve it, you need to understand, you need to do some guesswork. And let me just wait a little bit so that see that, can you do that? Can you find or imagine a function based on good reasons so that the derivative of that function is this function?
ln x squared plus 1.
Yes, thank you very much. Thank you. So the reason is this. Do you remember, if I ask you, what is the derivative of ln of u? Thank you very much. It was a very good guess. So this combination is very famous, and you need to know that by heart. This is at the level of your lesson, yes? ln of u, if u is a function of x, it becomes equal to the derivative of u in the numerator and divided by u. So this combination, I would say that it's better to know it by heart, okay? If I have the derivative of a function in the numerator and the function itself in the denominator, this combination is a primitive is of this type. So if I ask you what is a primitive function, so let me write it somewhere for you. We did it before, if you remember. I remember Khulud answered actually that. So what is the primitive function? That was my question, the first example in the previous session. And then you answered ln of f of x. And that's exactly the same story. But in the book, when you have this formula that what is a primitive function for L for 1 over x, it is written ln of x, and they have mentioned that x is positive. If you go back and review my lectures on derivative of logarithmic functions, you see there that I told you that you can relax this condition by saying that the derivative of ln of absolute value of x is also the same 1 over x. If you have forgotten and you are interested, you can go and review that video. And so it means that I don't need to limit myself to positive values. I can just limit myself to non-zero values, even negative numbers. So of course, x cannot be equal to 0 because ln of 0 is not defined. 1 over 0 is not defined either. But if x is not equal to 0, this is okay. But still, ln of x is not okay, because if x is negative, ln of x becomes undefined. Ln of a positive number only makes sense in the real number system. Okay, and then I showed that the derivative of ln of absolute value of x is again the same function. So if you have this combination, I want you to learn, because we don't know if f of x is positive or negative. To make sure that everything is okay, let me add this one to what I told you in the previous session. So if you see a combination of a fraction whose derivative, the fraction, and then you see that the derivative of the denominator appears in the numerator, always and always think about this combination. If you want to know it precisely, I would write the absolute value. But of course, at the level of your lesson, if you ignore absolute value, no problem. But the correct way is to put this absolute value. And exactly, you see, this is happening here. This function here, the derivative of this function is 2x, which appears in the denominator. So if I want to find primitive function for 2x over x squared plus 1, this is somehow a guesswork, an educated, by the way, guesswork using this formula. So you write ln of absolute value of x squared plus 1. But here, this you don't need even absolute value sign. Why? Because x squared is non-negative plus 1 is always positive. If you don't need to emphasize that this should be positive. So because all primitive functions is required, so I have to put this constant, but then I can just simply remove the absolute value sign, because this is always non-negative and positive, and then that is the story. Okay, I brought this up in an example because I saw some problems in the book related. Let me just go a little bit around that and now see how is it going, okay? So, for example, if I ask you this question, do you remember when I was talking about primitive functions, let me remind you, we had a table, we had f and the capital F. I was able to talk about sine kx. Its primitive function was negative 1 over k cosine kx plus a constant. And the same thing we talked about cosine. This becomes 1 over k sine kx. Okay? And then if you remember, let me write it here again. If I want to continue it here, I didn't write tangent of k of x here. I wrote tangent of x over there because if I ask you, tell me a function whose derivative is, so it means that then I wrote 1 over cosine squared x here. Yes, do you remember? Because if I ask you what is a function, so I'm a little bit confused here. So let me think a little bit. Yes, yes. Yeah, that's correct. So that is the way that I wrote it, and it was correct. If I ask you, give me a function whose derivative is equal to 1 over cosine squared, then you would say that is tangent of x. You see, the reason that this will work, I was a little bit confused, sorry. I lost my concentration looking for the classroom. So here, if I take the derivative of the right-hand side function, it becomes the left-hand side function. If that is the case, the right-hand side function is called a primitive function for the left-hand side function. So here, if I take the derivative of tangent of x, if you go and review my lesson, the derivative of tangent of x is 1 over cosine squared x. So I would say that tangent of x is a primitive function for this combination. Okay? And then I told you that there is another formula. Some books write it as 1 over cosine squared, and some books, they write it as tangent squared, 1 plus tangent squared x. But now I want to add tangent of kx here. This is not in the formula sheet, but the book has talked about that later. So let us talk about that. So first, let me make it first simple. I just want to ask you, can you tell me a primitive function for tangent of x? Okay? So what is a primitive function for tangent of x? I'm asking you, give me a function whose derivative becomes tangent of x. That is not among our famous functions. You need to construct it. But this idea will help you. Is that understandable? So let me write it in this way. It becomes primitive function. Instead of tangent of x, I can write sine x divided by cosine x. Do you agree? This is the meaning of tangent. I hope that you understand that this is somehow this combination with a minor problem. Is this fraction of this type? Can you assume that this fraction is of this type u prime over u? I would say 99% yes, there is a minor problem there. We have to solve that minor problem. It is not exactly this form, because if I take the derivative of cosine, it becomes a negative sign. If that negative sign was taken care of, then I don't have any problem. It is exactly of this type. Yes? So, but that's a minor problem. Why? Because I can write it like this. I can write primitive. I apply a negative sign there. Of course, I cannot just bring a negative sign out of my pocket and put it there unless I make it up, yes? So I put a negative sign here. So then you know that this negative sign will cancel that negative sign. Why? Because I told you, primitive function of a constant number multiplied by a function is equal to constant number multiplied by the primitive function of f. So if I take this c to be equal to -1, then this becomes primitive of minus f, and this becomes minus primitive of f. So remember that if you have a minus sign under the primitive function operation, you can pull it out exactly because I can pull every constant out. So here, I want you to understand this equality is a right equality, because this minus sign in principle can go out, and this will cancel that minus sign, and I will get my expression back. So what I have written here is 100% correct. But what was the point of doing that? Because this combination is now exactly u prime over u, yes? where I choose u. So if you choose u to be cosine x, u prime becomes minus sine x. The derivative of cosine is negative sine. And then you see that this is exactly the combination of u prime over u. When it becomes u prime over u, I know what to do. I put this negative sign here, so it becomes equal to minus. And then it becomes ln, absolute value I put here, and then I put u there. Okay? So what is u? U is cosine. So this becomes this. Okay? So this is why you don't see it in the table. But if I want to have it, I have also a k. I hope that you understand that you need to divide by 1 over k. And then you have a negative sign. Then it becomes ln of absolute value cosine kx. So let me write it here. Primitive function of tangent of kx is equal to minus 1 over k, and then ln of absolute value of cosine kx. And now, of course, if you are interested in all of them, you add a c at the end. So you see, it was at the level of your math lesson, so you can solve it. And I saw that when you go further, when we go to integrals, there are some questions, level 3 questions in the book, that if you want to solve them, you have to understand this idea. Okay? So for example, to make sure that you understand what's going on, let me write another example. And please interrupt me if you don't think it's clear. Let me ask you, is that clear? Is there something that I need to describe for you more? Okay, so let me write another function here for you to see how this goes. So let me write, for example, x to the 4 plus 2x to the 2 plus 1. Probably this is a bad example. Let me change this number to 5. So otherwise you can simplify the function. Just wait a moment so that I can confirm that everything is right. Yeah, so this function. It seems complicated, but the idea is more or less the same thing. Okay, can you help me to solve the problem? Can you detect the same kind of pattern there? A function in the denominator. First of all, this pattern only works if you have a fraction involved, but very particular type of functions. The functions whose numerator is somehow the derivative of the denominator. Of course, this is not exactly the case, because if I take the derivative of the denominator, it becomes 4x to the 3 plus 4x. Okay? You see, this is not exactly there, but you can do something similar to this idea to solve the problem using the same pattern. What can I do? So let me write it for here, and I wait for you to answer. So primitive function Okay, so what should I do? I realize that the derivative of the denominator is this expression. This is not exactly what I need, but it is not hard to see that if I pull a 3 out, then I will have that combination, yes? So what I do, I would write primitive. I pull a 3 out, and then, I mean, even though I can factorize more, but don't miss the goal. The goal is not factorization here. The goal is to make the pattern right. So I pull a 3 out. So what is left for me is 4x cubed and then 4x. And then the denominator is x to the 4 plus 2x squared plus 5. But I just told you here, it's still on the board, yes? Let me just write it again if that's messed up. So if I have a primitive of a constant multiplied by a function, that multiplicative constant can be taken out from the primitive operation. So this becomes that. So it means that now I can pull this 3 out. So this becomes 3 primitive function of that combination. But that combination is exactly the right one. Yes? So you see that this is exactly u and u prime. So if I take this to be u, if I take u to be x to the 4 plus 2x squared plus 5, then u prime is 4x to the 3 plus 4x. So this combination is u prime over u combination. So the answer becomes ln. I have a factor of 3 here. So this becomes 3 ln of absolute value of u, which is x to the 4, 2x to the 2 plus 5. But again, I don't need any absolute values, and I have to put a constant of integration here. Because x to the 4 is non-negative, 2x squared is non-negative, when I add 5 to a non-negative number, it is definitely positive, so I don't need to overemphasize on that by putting the absolute value sign. I remove it. So this is also something like that. I will just give you one more example and we go to the new lesson. So number 4, f of x is equal to, so let us make it x to the power of 3 plus so something like this. 7x squared multiplied by 7x divided by x cubed plus 3 over 2x squared plus 1. At the level of your lesson, if you face some fraction like that, you need to remind yourself of this trick because you haven't studied any other tricks. So, yeah, so you need to find a pattern. So what you need to do is to see that if this expression is somehow the derivative of the denominator or not. So let us take this one to be u and then differentiate it. It becomes 3x squared plus 3x. Okay, so I face a problem. Instead of having 3's here to make the right combination for me, I have 7's. But is it a dead end or there is some way out of it?
We can still multiply by 3 over 7.
Exactly, so that's the point. So what I do, I would say that primitive function of this function is desired. So what I do, I understand by this analysis that I need 3's, not 7's, but I have 7's. So what can I do? Let me write 3's there. But I am not allowed to change the problem and solve it. I have to solve the same original problem. The original problem have 7's here, not 3's, but it is clear if I divide by 3, I get rid of these 3's and I multiply it by 7. So hopefully now you agree that this equality is a legitimate equality. because if I factor a 3 out, that 3 which comes out will cancel this 3, and there is a 7 left. But I multiply, I will get this back. And now everything is clear. This 7/3 is a multiplicative constant. I can pull it out from the primitive operation. And then what is left for me is exactly the combination that I desire. Yes? Okay, so then what happens? It becomes 7/3. This becomes ln of absolute value of u. But u is this guy. And then I put a constant at the end. But here I have a constant there, and I am not allowed to remove the absolute value sign here, because even though 1 is positive, x squared is positive, but if I have a very huge negative number, for example, this will dominate and make this one negative, but I am not allowed to let this argument to be negative for ln. So absolute value here is necessary. Okay, so this is what was left from the previous discussion. I want to see that if there is no questions, I can start the new lesson today, definite integrals. In your book, they have written just simply integrals. And the reason is that we call it definite integral, because primitive functions are called indefinite integrals. And then, so we have 2 types of integrals. Primitive function is an integral. And then this integral that we want to talk about is also an integral. So we call one of them definite integral, the other one indefinite integral. But here you don't have the notion of indefinite integrals. That is called primitive function. So we can just say integrals. And here you can assume that this new lesson is a totally new lesson, apparently completely and totally unrelated to the notion of primitive function. But that was the genius of Newton, who discovered the connection between these 2 ideas, and little by little I want to talk about that. So today's lesson, I want to describe more or less every detail given somehow in the book, but you really don't need to be worried, because it turns out to be complicated. So I will more or less study about the history and the development of integrals to see where these ideas are coming from. And I want you to feel that solving the problems using these ideas that we develop is quite hard and sometimes impossible. And then you will appreciate the method that Newton discovered to solve this problem. Okay? So I'm just telling you that what is coming might be quite complicated. I want you to see it as a person who has chosen Technique or Natur program in high school, but it is not something that you need to be worried about for the exam or something like that. So you can just relax and try to understand what's going on, okay? Yeah, so let me clean everything. I don't know, did you ask a question? Yes, please. Yeah, please speak louder, so my speaker is not that high quality here. So what is your question?
So I wanted to ask.
Yes?
Where do you put absolute value?
No, absolute value, you put absolute value if the expression inside is sometimes positive and sometimes negative, and you want to make it positive all the time. Because if I ask you what is ln of -2, it is undefined. So when I talk about ln of x, then I would say that in primitive functions, if the problem itself is ln of x, in the problem itself, you are not allowed to change the problem. But when you want to find a primitive function and the answer is ln of x, because x can be negative or positive, and if it becomes negative, I will have problems for ln, I would put this one, because if you go back to listen to my lecture for when I was teaching logarithmic differentiation, I told you that the derivative of ln of x, this is in the book, the derivative of ln of x is 1 over x, but in the book they have emphasized that x should be positive, and that's quite right, because if you write ln of x in this form, x cannot be negative. So what is written in the book is this one, and it only works if x is positive. But I told you that, I have shown that to you if you want to see the proof. If you take the ln, if you take the derivative of this function again, it happens to be the same. But this formula is not just valid for positive x's, it is valid for non-zero x's. So this is the way that I am using it. So if someone asks me, what is a primitive function for 1 over x? If that person tells me that x is positive, I can write it ln of x, that's okay. But if someone asks me, give me a primitive function for 1 over x, and I don't guarantee that x is positive, I only guarantee that x is not 0, then if I write ln of x, I will have problems, because it might happen that x is negative and I'm writing ln of x, so I will write this one. So this formula is valid. This formula is good when you don't know if what you put inside is positive or negative. When I write ln of x squared plus 1, I don't need to put absolute value, because x squared is non-negative plus 1 is positive. If you write absolute value, it is not wrong, but you are overemphasizing. You don't need to do that, okay? And then in mathematics, when we don't need something, we don't just write it there. We want to write it in the most simplified version. For us, a pair of brackets is easier to understand than the absolute value. So I don't put absolute value, even technically I can. But if I have this situation, x to the power of 3 plus 1, if I want to find a primitive function, I am not allowed to remove the pair of absolute values unless someone tells me that this is positive. If I don't have any information about x, I cannot remove that, because x to the power of 3 plus 1, if x is positive big, it becomes positive, and if it is negative and big, it becomes negative. So I don't know, and I have to keep the absolute value. Hopefully I could answer your question. Did I? Okay, thank you. So let us now go to the new lesson. So something that I want to make sure that you understand is this simple notion of a partition of an interval, yes? So let me write this. Partition of a closed interval. So I just told you, just listen to me. You don't need to be worried about the complication that you might face in the board, okay? But it's better when you want to learn something, you need to understand it deeply. Okay, so what do I mean by partition of a closed interval? First of all, an interval is something like this. When I say closed, I am emphasizing that these are inclusive. Inclusive means that I have equalities as well. So the final points are included in the interval. If that's the case, I will call it closed interval. So for example, what happens if I have an interval? Let me just draw it here. So for example, let me start from 0 and let me go up to 1. 0, 1. For example, I want to partition this interval, the closed interval from 0 to 1, into 5 equal parts. If I do that, that is called the partition of this interval. It's a very simple idea, yes? What I want to divide it into 5, so 4 parts. 4 is easier. So what I do, it means that I go from, what is the length of this interval? The length of this interval is 1 minus 0. I want to divide it into 4 equal pieces. So I divide it by 4. It becomes 1 over 4. So I will start adding 1 over 4 at a time so that I reach to this point. I have 0, I add 1/4 to it, 1/4 to it. So I will go, for example, here. I will add a quarter to it. I will reach to 1/2, which is 2/4, of course. Let me write in the units of 1/4, easier to track. And then I add another quarter to it. It becomes 3/4. And then if I add another quarter to this, and I will reach to this point. So this set of 0, 1/4, 2/4, 3/4, and 1, I call it a partition of the closed interval 0 to 1 into 4 subintervals. This is called the first subinterval. This is the second subinterval. This is the third subinterval. And this is the fourth subinterval. Okay. So I can ask you, for example, take the same interval and now partition it into 5 subintervals. You don't need to be worried. What you need to do, you need to calculate the length of the interval, which is still the difference between these two numbers gives you the length of the interval, but this time you divide it by 5. So what you get 1/5, okay? And then every time you add 1/5 to the previous number. So you will start from the first number, which is 0. You add 1/5 to it. It becomes 1/5. You add one more 1/5. It becomes 2/5. The next one, it becomes 3/5. The next one is 4/5. The next one becomes 5/5, which is exactly 1. Okay? So this means that now I have 5 subintervals. The first subinterval is between 0 and 1/5. The second one is here. The third one is here. The fourth one. And finally, the fifth one. Okay? And it doesn't matter that if I want to, what are these numbers? I can ask you to partition an interval from, for example, 2 to any number. For example, 2 to 7. So let us give you this example. I give you the interval from 2 to 7. And I ask you divide it into, for example, that number is denoted by n. I ask you to do it into, let us make it a simple, 6 intervals. Okay, so n, this little n denotes the number of intervals that I am asking you about. So I'm asking you to partition this interval into 6 subintervals. First, what you need to do, you need to assume that in general this is A and this is B in general. So you need to find the length of the interval, which is the final number, minus the first number, divided by the number of partitions that is being demanded in the problem. I would call it n. And this is denoted by delta x. It is the length of each subinterval. These are the symbols. So delta x, you will see it in the book if you open the page. I'm just going to it. So delta x is the length of each one of these subintervals. B is the final point of your interval. A is the initial point. It is clear that the difference gives you the length of your interval. And then it is mentioned that I want to have 6 subintervals or 6 partitions. So what I do, I divide it by n. So I calculate. So this formula is good to know. So let me put it in a box. But for this problem, I continue to calculate it. B is 7, A is 2, and n is 6. So it becomes 5/6. So it means that at each time, I need to add 5/6 to it. So, okay, I will start from 2. The next number is 2 plus 1. And so it is 2 plus 5/6. Yes? The next number is 2, is this number plus another 5/6. So I have already a 5/6, so it becomes 2 times 5/6. The next number is 2 plus 3 times 5/6. Yes, and then I go plus 2 plus 4 times 5 over 6, and then I will have 2 plus 5 times 5 over 6, and finally 2 plus 6 times 5 over 6. Yes, but this is the end of the problem, because 6 times 5 over 6, 6 and 6 are gone, I have 5 and 2, it becomes 7. So I don't need to write it in this form, this is actually 7. Okay? So it means that if I draw a diagram for you to understand it better, my starting point was 2. Each time I am adding 5 over 6 to the previous starting point. So I don't know, for example, assume that from here to here is 5 over 6. I'm exaggerating a little bit so that you can see it. And then here, if I ask you what is this point, this is 2 plus 1 part 5 over 6. Again, I add one more 5 plus 5 over 6 to it. Then I reach to the point which is 2 plus 2 times 5 over 6. Yes? And then you can continue, yes? So again, you can continue 2 plus 3 times 5 over 6. But the important thing is that I am still adding the same value every time. And then if I continue this, I will reach to the value 7 at the end. Okay? So one thing that I want you to understand here is what happens. Let me write these formulas here. If I want to solve it generically, so I would say that assume that this is your axis, and then you have a point A. I'm talking about the general case. A and then B, and then they ask me to partition this into n subintervals, yes? Let us see how can I find a formula for these numbers here. So how can I do that? First of all, I need to find each one of these lengths. Yes? So how should I do that? I would say that delta x, it's still on the board, delta x is b minus a divided by n. So the first number, let me call it x1. The second number, let me call it x2. What is delta x? I add one delta x here, I will get here. I get another, I add one more delta x, I here. So it means that for x1, I add 1 delta x. For x2, I add 2 delta x's. For x3, I add 3 delta x's. Okay, and then I will continue. So if I ask you, what is x1? I will write and clean it. What is a1? What is x1? x1 is a plus 1 delta x. If I ask you what is x2, x2 is a, but how much you are deviated? You have 2 delta x's to add. So 2 times delta x. And then if I have x3, it is a plus 3 delta x's. Okay? And so you see that this index here matches this coefficient here. So if I ask you what is the formula for the nth subpoint, so for the nth point of the partition, you would say that, sorry, let me write k. The kth one, you say that this is a plus k times delta x. As simple as that. And if you want, you can write a formula for that. It is a plus k. Instead of delta x, I can write this expression. So this becomes b minus a over n. Okay? Let us see what happens if I put 0 here. If instead of k I put 0, I will get my original point back. So another name for this, I can call it x node. And let me see what happens if I put k equal to n. Of course, n and n will simplify. B minus a and a will be added. I will get the final point. It is not surprising. Yes? Because I start from here and there to here. So here I can write that k is somewhere between 0 and n. K belongs to the set of integers, non-negative integers between 0 and n. So this is also, I put it here. One more thing is that I want you to understand this is called the first interval, first subinterval. This is called the second subinterval. This is called the third subinterval. So if I ask you what is the kth subinterval, you can immediately answer that. So what is that one? The first one is between x0 and x1. The second one is between x1 and x2. The third one is between x2 and x3. So the kth one is between xk minus 1 and xk. Okay? So as simple as that. You might say that why they are useful. They are abstract notions, I understand, but I will come back to it, okay? Why these are important for our purposes. Okay, so far, I do not have any functions involved, okay? I'm just talking about only the x-axis, and I'm just talking about abstract notions of intervals. These are simple calculations. I need it only once for this lesson, if hopefully we can finalize everything today. Otherwise, I will continue next session. So these are the informations that I write on the board once to make you understand what is the core of this subject, and I remove it. And thanks to Newton, we don't need to go through this mess all the time. We can solve the problem easier. Okay? But the formula that I want to come from it is written in the book. So I want you to have a good understanding, even though we don't use it at all. Okay, now assume that I have also a function. Okay, so let us do something like this. For the time being, let us consider a function, a continuous function, and let me make it simple. You only talk about continuous and differentiable functions. Continuous means that I can draw the graph with one pen stroke, and differentiable means that there are no sharp points. So assume that you have something like this, and this is the graph of your function, not the whole graph, the graph between 2 points. So let me write it, for example, here. So this point, let us call it A, and then let us go up to this point, B. And if you don't mind, let me just ignore what is going after that and before that, yes? Yeah, it was easier. I teach this subject when I am at home using GeoGebra. But anyway, let us do it traditionally, when people didn't have these kind of technologies. So here, and they invented all of these things, by the way, at that time. Okay, so here, the first motivation that people start thinking about integrals is that people from probably ancient times were very interested in measure of areas. Okay, of course, we know a lot of formulas, even from ancient Greeks. So, for example, you can find the area of a triangle, area of the rectangle, parallelogram, and things like that. But usually, the reason people were interested in finding areas is because of land survey, yes? And then the nature is not very usually kind to us to give us a very organized and regular shape. So they wanted, for example, to measure the area of a piece of land so that the border of that land might not be very organized or regular. So in principle, they wanted to solve this problem. If I have an arbitrary curve here, is there any way for me to find the area bounded, restricted between these two vertical lines? Of course, this is also a restriction. We can relax later. So I have four borders. 3 of them or still the simplest shape in geometry, which is a straight line. The other border is a curved one. Of course, we know about the circle or whatever, but this is a completely generic curve. I know the function, but I don't have any control on the graph anymore. So is this possible for me to come up to with an idea so that I can not measure, to calculate the exact value of the area under this curve, which is limited from left to this straight line, from right to this straight line, and from below to the x-axis. All of them are straight lines except the curve itself. So that was the idea. Okay, so the idea might be is familiar for you. I was also teaching some part of it in Math 3C. But if you want to do that, okay, so this problem probably is too hard for us. You might say that let us do some approximations. Okay, so let me do not partition this interval at all, and then find, for example, the minimum value of my function here somewhere. So the minimum value occurs here. And let me construct a triangle whose length is equal to that and its height is equal to this here. Okay? So if I construct that, so I don't know, for example, let me call this point C. I'm just concentrating in this. Okay, first of all, I want to ask this one, I want to clean this because I am not partitioning this at all. I do not have any subintervals. The reason that I draw in the diagram because I want you to get the feeling that this is the minimum value, and I just constructed this rectangle. If I ask you what is this length, this is easy for you because you would say that I put c in the function f of c, this becomes f of c. Okay? So now let me clean this one. If this is f of c, this one is also f of c. Okay, so let me clean this one not to disturb you. And now, is it possible for you to measure the area of this rectangle? The answer is yes, because these numbers are given to me. So what I do, I calculate this length, which is simple, b minus a. And because the function is given to you, and you are able to find this point of minimum, for example, you don't need to be very specific about that point, you will see later. So then I will put that number into my function. I get a number which plays the role of the height of my rectangle, and I multiply f of c by that. If I ask you from geometric point of view what you have calculated, hopefully you immediately tell me that I have calculated the area of the rectangle, which is colored in my picture. So this is the area of my rectangle. Of course, this is better than nothing, but you can immediately realize that there are two big differences between the area that I desire to calculate and the area of this rectangle. Yes? So for example, you see immediately I am just ignoring the area of this part, and I'm also ignoring the area of that part. So it means that this is not exactly, you don't need to be very smart to see that this is not exactly the area that I want. And if I write this, I would write this approximately equal to this one. And then you might say that, okay, even though approximation is now okay, but what is the error that I make in this calculation? Is it a good approximation for this area or not? Archimedes, actually, 400 BC, came up to this very intelligent idea. He said that, okay, let us increase the divisions. Here, I just did this area by concentrating one piece of rectangle. Why not? Let me concentrate on two rectangles. Of course, this is historically wrong. He used triangles for these approximations, but the core essence of the idea was the same. Okay, I want to clean a lot. Okay, so this, let me keep it here. And he said that, okay, now let me divide the interval into two pieces and do the same thing, not for one rectangle, but for two rectangles, yes? Let us see how this will go. In GeoGebra, I was able to convince you that this method is actually working very, very nice, but it is hard to, it might be some point, unfortunately next week you're also here, so might be I can bring GeoGebra into the classroom. So let us see how it goes. So, okay, this is the first approximation. Now let me partition. You see, now this idea comes into the game. Yeah, I want to partition this interval into two subintervals. So what I need to do, just forget about those calculations. I need one extra point exactly in the middle because I want to divide it into two pieces. I want to follow the same notation. This is called x naught. This is called x2, yes, because I have two subintervals. This is, sorry, yes, that is x1. And now, don't think about this. Separate your problem into two problems, yes? What you do, just concentrate here, because if you can calculate this area, and you can calculate this area, it is clear that the total area that you are interested in is the sum of these two areas. It's clear. So let us do more or less the same ideas here. Let us stick to minimum, okay, for the time being. Let me find the minimum of my function, forget about this part, here. Again, this is the same value. Yes? So let me construct this rectangle, but I do not go beyond that in subinterval. Just stick to it. And let us go to the next interval. Again, do the same thing. Let us concentrate on the minimum. So what is the minimum of this function if you limit yourself here? It's clearly happening here, yes? This is the minimum that occurs on this interval. Complete your rectangle using that. Okay? And now the area, let me call this one area 1, area 2. If you continue, reach to area 51, yes? Yeah, so but we have only two of them, area 1 and area 2. And then if I ask you, what is the area of this rectangle? Let me write it area, the total area that I am interested in. Let us keep this letter. Let me just write A1 plus A2. If I ask you what is A1, in this case, this is exactly the same number. Okay? So let me write F, this one C1. Okay? And then multiply it by the length of this interval. But the length of this interval is x1 minus a. And then plus, here, I will have f of x1, because this would be the length. And then I multiply it by this length, which is b minus x1. Okay? So this is the area in this part. This is the area 1, and this is area 2. I am adding them. This is the number that I get. But here, let me make it more simplified. So this one is delta x. Do you remember exactly to that? This is delta x. This is also delta x, because I am assuming that I am partitioning it into equal pieces. Both of them are delta x. So you will get f of a number, let me call it number C1, delta x, and let me call this one number C2, delta x. If you ask me what is C1 and C2, I would say those are numbers in the interval which give me the minimum value. Here, the minimum value occurs somewhere in between, so C1 is different from A and x1. But here, the minimum coincidentally occurs at x1. So in principle, C2 is the same of x1, but because I want to have the same notations all over, so let me write C1 and C2. But if I ask you, show them on the picture, for C1, you show it here. For C2, you show it here. Okay? So what I am doing is just calculating the area of two rectangles. But is the area of these two rectangles is equal to the area that I want? Exactly, again, no. The area that I want to calculate is approximately equal to this. But let us see what are the deviations. This is I want you to understand. So you see, the deviations are this small part, this part, and that part. Unfortunately, I had to erase the picture, otherwise it would never end. But I hope that you can convince yourself that these errors that I am making now, even though there are errors still, but these errors in total is smaller than the error that I made in the previous picture. And then suddenly it becomes clear, why should I stop with two partitions? If I want to have a better approximation, I can increase this into more intervals. Yes, this idea I will use GeoGebra to show it. Might be you don't think that this is working, but if you see the demonstration on the display, you agree with me, this is not actually a naive way. Even if I do it, for example, 1,000 times, it's quite, it's not possible for our eyes to detect the difference. Okay, I will show it. But even you're a mathematician, you are imagining things, why you should stop when for 1,000. You can imagine I go to 1 million. You can imagine you go to infinity. And hopefully you agree with me, if I start increasing these subintervals to more and more intervals, all the time I will have errors. But this I want you to understand. The error that I make at a time becomes smaller than the previous time when I have a lower number of partitions. Yes? So I want to wait. Do you understand? Do you have the correct feeling for that? Is that understandable? That if I increase the number of partitions, I have still errors, but the errors are getting smaller and smaller each time. Is that okay?
Yes.
Okay. So then it means that let us use a symbol for that. If this is only two of them, what happens if I go to three of them? Then I will get a similar term. If you want, you can write f of c1 delta x plus f of c sub 2 delta x. Next one, if I divide it into three partitions, it becomes f of c sub 3 delta x, and etc. Okay? So, and then usually we will have big sums. The thing that usually we think about is the summation notation. Yes? So why we should stop here? So for example, here, I can write it as sigma k goes from 1 to 2 in this case, and I will write f of c sub k delta x. Hopefully you agree with me. If I put k equal to 1, I will get the first term. If I put the second number 2, I will get the second term. And these are the only ones, so I stop and I add them. So this can be summarized in that form. Okay? So if I go to the third case, then still A, the total area that I want to calculate, is approximately, but this time a better approximation, with summing three rectangles. All of them will have the same type of a structure. It would be f of some value, which gives me the minimum of my function in the first interval, multiplied by delta x. The second one, f of c2. This c2 is a number within the second interval, so that it gives you the minimum function there, multiplied by delta x, and then I will have an extra term this time for the third subinterval. And now it is clear that I can write this as a sigma k goes from 1 not to 2 up to 3 this time, f of c sub k delta x. And as I told you, why we should stop for 3 terms, because my goal is to have a better and better approximation for my area. Okay, so what I do, I would say that if I continue, then I will have a better approximation if I increase the number of subintervals. For example, let us consider it up to n subintervals. You see, I have reserved this symbol for that. Okay, then hopefully what you can write the same structure sigma f of c sub k delta x, k goes from 1 to n. Yes? And because this, so now let me call this, yeah, that's correct, that's good. So this is the area that I find it when I go up to n. But now intuitively, just intuitively, tell me, what do you think if I want to have the exact value of A? Every time that I am increasing a subinterval to my partition, I am getting a better and better value for the real area value. Okay, now assume that you want to don't think about practical problems. Just imagine. If I want to have the precise value, if you just want to imagine wildly, what do you imagine? How should I do that? Because, by the way, calculating these things are getting harder and harder. I'm just putting this under the rug right now because you see, this is a tedious and boring calculation. So assume that I just write a number there, but I want you to feel it with your flesh and bone. Okay, so if I ask you to do it 1,000 times, then probably you definitely will give up. I am not talking about practicalities here. I am talking in principle. So in principle, what do you think if I want to have the precise value?
We have an infinite number of subintervals.
Yes. So yes, in principle, I should have infinitely many subintervals. So it means that the area that I am looking for seems to be the limit of this expression when I am sending n to infinity. So this means that the area apparently becomes the limit of this sum, f of c sub k, delta x, k goes from 1 to n, but I do not stop at any particular number. I am brave enough to send it to infinity. Okay, so this formula is in the book somehow. I want you to understand where this formula is coming from somehow. Do you have any questions so far? At least you see that there are many things that we cannot address at this level. The first thing, how can I calculate this limit in the first place? Because it's not possible to sit down. If your patient might be, you can do it, I don't know, 1,000 times or even 1,000,000 times, but let alone, how can I go to infinitely many times? So even though this formula is reasonable to agree on, but it is practically useless. I was a little bit wrong to say useless, but then I can show that in principle, you can use this formula, okay? And this one, I really want you to see it. Just try to enjoy it if you like mathematics, but that would be definitely not part of the exam or something. Even this formula is in the book. I want you to understand that. I will not give questions regarding that, okay? This sum in mathematics is called the lower Riemann sum. Riemann is a mathematician, very genius. Unfortunately, he died when he was 39. So it's a really brilliant German mathematician. So this kind of sums are called Riemann sums. Okay, I just want you to know this as an extra piece of information. Okay, I just mistakenly told you that this is useless, but not that useless. Let us try to enjoy this formula a little bit to, for example, calculate one area that we already know, but using this trick. It means that we are making life harder for ourselves, but we also enjoy it if we like mathematics, okay? And then you will understand why facing and using this formula all the time is hard. I don't know if we have enough time, but let me hurry up a little bit because that would be a pity. So if I don't show this one to you. So let us clean this one. I want to exaggerate the picture a little bit so that you can see it. So let us call this function y equals to x. Of course, this is the bisector, and I'm exaggerating it. Let us take this one 0 and take this one 1, and I want to measure the area of this, triangle. Of course, you really don't need to understand that formula because it is super simple. You know the formula for the area of the triangle. So from here to here is 1 unit. Y is equal to x. X is equal to 1, so this length is also 1. If I want to find the area, it's super simple. I multiply 1 by 1 divided by 2, finished, 1 over 2. Okay? So hopefully everyone agrees with me that the area of this triangle, which is a right angle triangle, is 1 over 2. But let us try to use this formula if possible. So what I have to do, I have to subdivide the interval to infinitely many intervals. But I cannot do that. I will do it to n subintervals, and then I will send n to infinity at the end. Okay, so what can I do? So for example, let us try to do it. I concentrate only on one of these intervals because then it might be hard if I want to draw all of them. So let me consider, I am partitioning from 0 to 1 to n equal pieces. And let me concentrate, this one is the kth interval. It is reserved here. You see, the kth subinterval is an interval between x sub k minus 1 and x sub k. So let me call this one x sub k minus 1 and then x sub k. Okay? And then what I want to do, I want to calculate this Riemann sum, sigma of fc sub k delta x, k goes from 1 to n. Yes? Okay, so how can I do that? F of c of k. Do you remember I told you that c of k is the number within the kth interval which gives me the minimum value. Because of the nature of this function, the minimum is attained when ck is actually equal to xk minus 1. C sub k is the number within this interval so that it gives you a minimum value for the function. But because of the nature of the function, which is increasing all the time, if I concentrate myself here, everyone agrees with me in this, within this interval, the minimum value occurs at this point. So ck in this problem is xk minus 1. So then if I continue this, this becomes sigma k goes from 1 to n, f of ck which becomes f of xk minus 1 delta x. Okay, so let me just do these things quickly. I would have, if the time is finished, I will continue recording the video, but if you have another lesson, you can move on to the lesson and then you can watch the rest of the video, okay? Because I want to finalize this. Thank you. Okay, so let me put these things. For the delta x, let me calculate delta x. Delta x has a formula here on the board. B minus a divided by n. But what is b? B is the final point of interval. What is a is 0, the initial point, and then I have n. So delta x is super simple. It's just 1 over n in this problem. Okay? And then what is x sub k minus 1? Okay? xk, I have the formula for xk on the board. You see? I have reserved them for this purpose. X sub k has this formula, so let me write it in front of our eyes. A plus k times b minus a divided by n. So let me put the numbers inside. A is the initial point, 0. B is the final point, 1. So this becomes 0 plus k, 1 minus 0 divided by n. So if I ask you what is this, the calculation shows that this is k over n. So if I ask you what is x sub k, you would say it is k over n. But I do not want x sub k, I want x sub k minus 1. So this gives me, I have to replace k with k minus 1. Then it becomes k minus 1 divided by n. Agree? And now I want f of x sub k minus 1. This is my function. F of x is equal to x. Okay? So f of x sub k minus 1, because my function f of x gives me the same value for x, f of x sub k minus 1 gives me the same value of x. Okay? And then I know the formula for that. So let me put everything here. So the area that I'm looking for is the limit of this sigma. Sigma k goes from 1 to n. I have to replace x sub k minus 1 is this expression multiplied by delta x, which is 1 over n. Yes? And n goes to infinity. Okay, let me calculate this one for you. So this n and that n becomes, if I multiply them, it becomes k minus 1 divided by n squared, and k goes from 1 to n. And I want to take the limit when n goes to infinity. Okay? So let me open up this sigma for you. So sigma, when I put k equal to 1, this becomes 0. Yes? 0 over n2. When I put k equal to 2, it becomes 1 over n2. When I put 2, it becomes 2 over n2. And I continue until I put the final limit, which becomes n minus 1 over n2. But this is not a hard one, yes? Because, first of all, the denominators are all the same. So let me continue here. The denominators are all the same, so I can combine them into the form of one sum. The denominator is n squared. And then I will start adding the numerators. 0 doesn't have any row, so I start with from 1. So then the numerator becomes 1 plus 2 plus 3 plus up to n minus 1. N goes to infinity. Hopefully, this famous sum is something that you know from your studies. You remember when I was teaching you mathematical induction, I told you that this is a famous formula, and I wrote it as n times plus n plus 1 divided by 2. Of course, this formula is correct if I go up to n, but here I am going from 1 up to n minus 1. So what I need to do, I need to replace n with n minus 1. So it becomes n minus 1. The next one becomes n divided by 2. So I can continue and write this limit of n times n minus 1 divided by 2 divided by n squared. And n goes to infinity. Yes? So this n and that n are simplified. So then it becomes the limit of n minus 1 divided by 2n. You see, this n and that n are simplified. These two will be multiplied here. You will get that one. And I want to know what is this one. It's also something that you understand immediately. Let me divide this. I divide n over 2n minus 1 over 2n. N goes to infinity. Let me write it here. N over 2n can be simplified, so it becomes 1 over 2. But here I cannot do any simplification. I have to write it down. N goes to infinity. And I hope that you can immediately see, tell me what is this limit. I am making this n in the denominator of the second fraction very huge positive number. Yes? So nothing will be left when I reach to infinity. Yes? So this term will cancel, and what I get is 1 over 2. And that 1 over 2 is exactly that you were able to calculate it using this. So at least you see, this is not totally useless. We were able to find the area in this way, but you can now imagine what is happening. I have to do a lot of calculations. So at least this example shows that we are not totally out of track, yes? Because the ideas were reasonable, and I was able to practically use it at least for this simple, very simple idea, and I was able to get the same answer. And then, I don't know, next time, I think that's also good if I want to show you something non-trivial so that you don't know the answer, okay? So you don't know the answer. But let me finalize this problem. What would be the genius of Newton? Newton realized, you see, hopefully I want you to tell you something. You see, calculating this limit is tedious. For the simplest possible function, probably one of the simplest possible functions that you can even imagine, the calculations are tedious and horrible. Let alone the function becomes complicated. Then you can imagine what would be this one. And it becomes impossible sometimes. The reason that it was possible, because I had a formula, a closed formula for the sum that appears. In general, I do not have those formulas for generic functions. But let us talk about Newton's idea, and you can appreciate it immediately. He realized that you don't need to do this mess at all. Now this is the connection between this idea and primitive function, which was not known before him. He said that let us give me one primitive function for x. Everybody knows about that. It's 1/2x squared. As simple as that. And he said that put this number, the final number here, it becomes 1/2. Put the first number there, it becomes 0, and subtract them. You get your golden number. So, and then it turns out that this idea is very, very useful and practical for other functions that are complicated. Okay, so you see, this was very, very interesting. The topic of integrals deals with this problem. It was not clear before Newton that there is a connection between derivative, primitive function and the area. Now, even so, people were using this idea to calculate things, and it becomes very, very messy if the function is complicated. He said that, okay, if you can give me a function whose derivative is this, namely, if you can give me a primitive function, I don't have any problem with calculating the areas for you. I just put two numbers there, subtract them, as simple as that, you will get the same answer. Okay? So I just told you that don't worry about these details. I want you to see it in front of your eyes so that you have a deeper understanding of what's going on. We will continue the notion later next time. So thank you for listening. I will end this stream. I will be in Zoom if you have any questions. Otherwise, you can leave. Thank you very much, and sorry for being a little bit above the time. I lost a little bit of minutes looking for classroom. Bye-bye.